All right. Yeah, I see you guys all came early. Very interesting. Yeah, unlike previous semesters. So this is actually great. So I think Xuan was asking whether it's okay to skip tomorrow's lecture for the good weather. You know what? What's the benefit of doing online courses that you can more flexibly manage your time? Okay. But I can tell that some of you prefer to have online interactions with others. Yeah. So that kind of motivates you better to learn. But some of you, I can also tell that you prefer study alone, very independent. I can tell that also from how you guys did in exam one. Okay. So I did not add the announcement here because I'm actually not quite sure. So we are almost done grading exam one. Chances high that we release the grades by Friday. Okay. If possible, we'll try if we can release it tomorrow afternoon. All right, hi, welcome back to another episode of Introduction to Computer Networks. We do have PA5 doing, but as you guys know already, PA5 is just straightforward, right? Create a loop. And so that you can allow uploading of files repeatedly. So it's kind of trivial if you manage to do PA for yourself. And we do have 5 quizzes. Yeah, I think 5 quizzes during this week. Today we'll have 2. Tomorrow we'll have 3. We'll see if we manage to go through all of them. And I do have a special announcement, which is number 4 here. 2 weeks later, Polly will need to be on a business trip, attending a couple conferences that Polly just need to go. Yeah, because I'm one of the steering committee members, and I haven't attended these conferences for more than 2 years, and yeah, I feel that I must go this year. Okay, and so Polly will be teaching from Boston. We'll see how it's like. So the advantage of teaching online is also that I can be anywhere around the world and I can still teach at the time that's designated. Okay, good. Oh, today is Xiaobai's birthday. Okay. Yeah, so why don't we all wish Xiaobai happy birthday? I think Xiaobai was one of the earliest saying good afternoon greeting to everyone. Okay. Yeah, happy birthday. All right, so now. Yeah, from Boston. Happy birthday, Xiaobai. Okay. Good. So today is very straightforward. We just have 2 topics and you're seeing them right on the topic list. Let's finish RDT 2.1 and talk about RDT 2.2. All right. And RDT 2.1, we've started talking about it last week, but after a weekend we might have forgotten about what's RDT 2.1. So here's a quick recap. Recall RDT 2.0, we have data sender and data receiver. Data sender sends data. Okay. That data can have bit errors. So receiver here, after doing the checksum, can discover whether there's error or not. If no error, send acknowledgement. If error, send negative acknowledgement. But you see, there's a flaw in RDT 2.0 because if data can have bit error, ACK or NAC can also have bit errors. So RDT 2.1 is there to address this issue. What if we also have bit errors in the reverse direction? And the idea of RDT 2.1 is simply this. In case the feedback packet, ACK or NAC, is corrupted, the sender just retransmit the packet anyway. Okay? Just like when the sender receives a negative acknowledgement, what does it do? Retransmit packet. Okay, so that would ensure that the data gets sent. But you see, there is a problem that rises for the receiver. Because if the corrupted feedback packet is a NAC, then no problem, right? NAC, sender needs to retransmit. But if it's the ACK packet being corrupted, sender here sends the packet again. Receiver will receive that packet 2 times. And it's not good to send duplicate data up to the application layer. This is reliable data transfer mechanism here. We should ensure that there's no error, but we should also ensure there's no duplicates. Okay. So receiver here obviously needs something else to tell whether this is a duplicate packet or a new packet. So that is the 1-bit sequence number we introduced to RDT 2.1. And that is what we were trying to show. The sender side of RDT 2.1 being twice big because we send packet sequence number 0, wait until we receive the acknowledgement for packet 0, then we start sending packet 1. And wait until we get acknowledgement for packet 1. Then we move on to send the next packet, which is packet 0. Which is packet 0. Okay, so that was essentially the sender side of RDT 2.1. So we have twice amount of states. Okay, after sending packet 0, that state, wait for ACK state there. There are 2 conditions. Okay, if the packet is NAC, or if the packet, the feedback packet is corrupted, retransmit. Okay, so the state machine looks a little bit special. Okay, today the first video is gonna introduce the receiver side finite state machine of RDT 2.1, and here it comes. And this is the receiver of RDT 2.1. You see, similarly, the number of states and transitions also doubled. We borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right. They are the mirror of each other. The difference is just that the upper left is handling data sequence number 0, expecting data sequence number 0. And the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACK corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering this condition, this transition. Okay, so receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0. Perfect. Let's extract the data, pass it up to the application layer, generate the ACK packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACK could be corrupted. So checksum here is to enable the data center to be able to check whether the ACK packet or the NAC packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition. Receiver here, go back to wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below. And this will go on and on and on and on and on. And when there's no data corruption, when there's no ACK corruption. Now, what if there's data corruption in RDT 2.0? Yeah, that's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. Generate a negative acknowledgement, but hey, in RDT 2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the NAC. send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT 2.0. The two transitions remaining, yeah, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay? That's when the sender retransmit sequence 1, thinking, hey, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. All right? So if that's a duplicate, no, that's not extract packet, that's not deliver, again, the same thing out to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, yeah, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and then can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So, yeah, this is RDT 2.1. All right, so what do you see being unique in 2.1's receiver? Yeah, these ACK and NACK packets will all carry checksums. Yeah, that's to allow the data center to check whether the ACK or NACK are corrupted, isn't it? And in the meantime, there are also twice the amount of states, and the receiver are checking the sequence number of the data. Yeah. So in case there's duplicate, do not extract data and pass it up to the application layer. Good. Next, let's go through a few examples and exercise RDT 2.1 sender finite machine, receiver finite state machine. Now let's use a couple very simple scenarios to demonstrate how the sender and the receiver interact. So this is our RDT 2.1, no error case, and scenario is simply first to send one packet, and then second, continue and send yet another packet. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is this: send one packet. Now, we're here at the starting state to determine what transitions to take. Let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send one packet. So obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's going to complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for ACK or NACK 0 state. Right? So very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event, and then take the actions, and then finish the transition and land on the ending state. All so let me repeat. Starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side, currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all 3 of them starts from the state here. Now, event is, yeah, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no error, so this one is not possible. So this one passed to this point, this one passed to this point. But there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0. Therefore, eventually this transition waits. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state. Wait for 1 from below. And now next, right over here, the receiver is generating an add packet and it's being sent back. So that's gonna trigger an add packet arriving back at the sender. So sender here currently at the wait for ACK or NAND 0 state. See, there are 2 possible transitions. So which of these matches the ACK packet with no error? Yeah, this one here. No error and it's ACK packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to the state. And there's nothing to be done here. No more packet being generated flying back to the receiver. So we could have stabilized this right here. So sender here, stop here. Receiver, stop here. Okay. And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side. Yeah, you guys are right. Okay, so that was a bug here in my configuration. Okay, let's see. Okay, I think the sound is coming. Yeah, good. Thank you. Thank you for letting me know immediately. Okay, good. So what I was saying is very straightforward. Let's continue from scenario 1, which was shown in the video earlier. And let's move on to do scenario 2, which is simply to send another packet. And let's see if the transitions we'll be taking are indeed T3, T12, and T4. And after scenario 1, the sender's state should be here, right? And the receiver should be here. Good. And so sender here sends yet another packet. So this is the starting state. Which transition do we take? What are the candidates? Well, you know what? Wait for call 1 from above. There's only one transition going on, which is T3. Okay, and T3 is essentially getting a call from above, and it will take us to this ending state. As a result, we then need to execute these events. This is generate a data packet carrying checksum, and the sequence number for the packet will be 1. Okay, this is wait for call 1 from above. Therefore, we generate packet 1, and we send the packet out. So there will be a packet going to the receiver, in fact. Okay, so yeah, indeed, T3 is triggered first. Now, receiver, we're currently here, getting a packet. What are the possible transitions? So we do have T12, T13, and T14 being candidates, don't we? And this packet, you know what, we have no errors. So let's see the 3 conditions, which one match? So the corrupt case obviously will not match, but we do have 2 cases, 2 transitions that are no corrupt, and therefore we need to tell what is the sequence number of the packet. And here, sequence number 1. Therefore, this one is ruled out, and we match this transition. We take transition T12. Indeed. And so taking transition T12, it's going to take us to this ending state, and we'll be executing these events. Extract data out of the packet. Cool. And then we deliver data to the application layer, and we generate an acknowledgement, which now carries also a checksum. And we send that acknowledgement out, and that's going to go to the sender. Sender currently here, ending state of the previous transition. What are the candidates? Transition candidates? There are 2, right? T4 and T6. This is an acknowledgement and no error. So receive a packet. It's not corrupted, and it's not a negative acknowledgement, therefore this one is out, and we therefore match T4. And that will take us to the wait for call 0 from above. That's our ending state. And the actions we take here is nothing. Okay, so that represents a null set. All right, good. So indeed, the last transition we take is T4. And that should prepare you guys for quiz 17. Okay, so this is again on the left, RDT, oopsie. On the left, RDT sender. Okay, RDT receiver, finite state machine. And scenario 3 in quiz 17 is this: send 1 packet, but this time we have bit error. Okay. But luckily, no more bit errors afterwards. All right, so scenario 3, that's star from here and here for the sender and receiver. Okay, now follow the same threads of thoughts as Polly just demonstrated earlier in the video, as well as in the illustration on the PowerPoint. And now, find your teammate, go to channel W8, quiz 17. You have 3 minutes to work on this. Okay, go on. Interesting. Yeah, thank you for letting me know. Interesting. So I need to adjust that setting during the video play. But for now, we're back. Thank you. So maybe we should go back to the questions because some of you guys asked a few questions. Okay. So I think first is Xuan was asking, is there a chance that packet 1 arrives earlier than packet 0? It's actually not possible because packet 1 can only be sent after packet 0's acknowledgement has already arrived. Okay, where did that happen? You see here, the acknowledgement packet needs to be accepted before sender can send packet 1. So packet 0 goes, and whatever, how long the sender will stay in this state, it can, take the T5 repeatedly, but eventually it needs to get out of the wait for ACNAC 0 state before packet 1 can be sent. Okay, this is why this RDT 2.1 is called stop and wait protocol. Okay, you make sure that the previous packet has arrived before you send the next packet. Okay, Tanya was asking whether the question is tricky. Yeah, no, it's just sending one packet, but after scenario 2, right, we have returned to these two states. Okay, so you will be starting from here as the sender and starting here as the receiver. So if we are sending one packet from here, what are the possible transitions we can take? Well, just one. As a result, we send packet 0. But if at the end of scenario 1, right, the sender is here and we get a call sending one packet, in that case, we'll be generating packet 1. All right, so these state machines, they look complicated, but it's exactly a machine. They will follow exactly what the state machine says. They are not clever. They do not judge things themselves. They just, match conditions and do whatever the condition says or what the event list says. Okay. All right. And so, yeah, I see that you guys all have T1, T15, T5, T11, and T2. Yeah, so I think that's also what I had here. So first of all, we start from the starting state at the sender end. Yeah, we call T1. That's the only transition. Okay. And we send packet 1. And we move to the wait for ACNAC 0 state. And that's going to arrive at the receiver and trigger the T15 state because it's corrupted. So it matches this condition here, isn't it? Okay, this one is not corrupt. This one is not corrupt. So this is the transition that's being triggered. As a result, receiver generate a NAC and send back the nag. And so that nag will go back to the sender. And sender currently here, what are the transitions option? T5 and T2. And it's a nag. Which one would it trigger? You got it right. It's T5. Right? So the second transition is T15. The third must be then T5. As a result of going through T5, the ending transition is, well, this is a loop back transition. Therefore, we stay here. And what do we do here? Retransmit the packet that we just generated. Okay, so SNDPKT, yeah, we send the same packet again. And so the packet will come back to the receiver. Receiver currently here. There are, again, 3 possible transitions. Which one does it take? Well, there are no more bit errors. Therefore, this time, the packet is going to come through and we'll consider the no corruption case. And this is packet sequence 0. So obviously, we take this one. So that is the 4th transition, T11. And as a result, we pass the data up to the application layer. We generated acknowledgement packet and send that back to the sender. And no more bit errors, therefore not corrupt, and it's an ACK. So final transition we take is T2. Very good. And now let's go on and try yet another quiz. Okay, 18. Now, so S4 here continues from S3. Okay, send one more packet. But there is a bit error in the returned ACK packet. Oh. So obviously, this packet get to the receiver right, and receiver returned an ACK packet. But this ACK packet here has a bit error. But afterwards, no more bit errors. All right, so this one seems a little bit tricky. So how about 5 minutes? Yeah, go to the Slack space, find the W8 Quiz 18 channel, and start working on it. Yeah, guys, you know what? I hope that my mic is on still now. Hopefully. Okay, good. Yeah, so you guys are very good. I changed the quiz a little bit, so you guys cannot just use the past years. Okay, great. Yay! Okay, so you guys cannot use past years as quiz solution. Yeah, so very good. So this is how I see whether you guys are really picking this up. Yeah, so I guess T3, T12, T6, T16, and T4. Yeah, that's exactly what I have as well, right? So following scenario 3, so the starting state of scenario 4 for the sender receiver correspondingly will be here and here. And we send one more packet. Okay, so we take T3 as the first transition, and we then land down the sending state here. And we generate packet 1 this time, and we send it out to the receiver. Receiver here receiving packet 1. Oh, what are the candidate transitions? T12, T13, T14. And hey, we already say, right, in the problem that the receiver sends back an acknowledgement. So which transition, sorry, I pressed the arrow a little bit too fast here. So which transition sends acknowledgement? So this one here and this one here. Okay. But you see, you receive a packet, and the packet sequence being 0, then we trigger T14, right? But obviously we're sending sequence number 1. So yeah, it must be this guy here, not corrupted, and sequence number 1, and an ACK packet being generated. So yeah, we trigger T12 next. As a result, we get the data and pass it to the application layer and generate the acknowledgement packet and send it back to the sender. Sender currently here. What are the candidate transitions? T6 and T4. And this is the ACK packet being sent back with what? A bit error. So which transition is the bit error case? Right, this is no corrupt, so obviously not T4. So we trigger T6 next. Okay, so that will send a packet and trigger T6 next. Oop. And what do? Retransmit the packet generated earlier. So packet 1 will be sent again back to the receiver. Receiver currently here will receive a data. No more corruption, no more bit errors. So among T11, T15, and T16, which transition will be triggered? Yeah, 16, right? Packet received, not corrupt, and sequence number 1. Perfect. So that will go to T16, and acknowledgement will be generated and sent back. And that would then trigger finally T4 and move to the wait for call 0 from above state. Okay, good. So we are on the same page. Okay, we're in the same picture. There's just one question from Carefree remaining. Is it possible that the corrupted NAC become ACK? It is possible, but with a very, very, very low chance. Okay, so that's the case when checksum fail. You might have multiple bit errors. Okay, where you change the ACK bit, change the bit such that the NAC become ACK, or the NAC packet looks like ACK, and it's still not being detected. Okay, so chances very, very, very low. All right, good. And that. With that said, let's summarize RDT 2.1. Now, this slide is called discussion, but what it does is really the summary of 2.1. So at the center side, what's being special is this. sender checks whether the ACK is corrupted. Okay. Now, in order to prevent having duplicate packets, the sender side now also assign a sequence number to the data packet sent. So it's either 0 or 1. And in order to track data packets carrying the sequence number, there are now twice the amount of states and twice the amount of the transitions. So the states somehow need to remember what is the expected sequence number. Receiver side, the primary function is to avoid receiving duplicate packets. So it would check the sequence number, whether it's a repeating sequence number. In that case, the packet is a duplicate. Okay? If that is the case, the data will not be extracted passed up to the application. It's just going to be discarded. But be careful. Receiver here seeing a duplicate, although not extracting data, not passing it up to the application, it will still what? Send an ACK out again. All right. Why? Because the former ACK or NACK being sent back to the sender. Yeah, only the sender knows whether the packet is corrupted. And if it's corrupted, the sender doesn't even know whether it's an ACK or NACK. So sender there is trying to be fuzzy and do the best thing that he can do, which is to repeat sending the data that has been previously sent. So receiver here needs to be more considerate. In case it's a duplicate packet, send back the ACK again, just in case it's an ACK packet being sent back and it's corrupted at the sender. Now at least the sender will be informed. Everything is okay and move on. All right, so that's RDT 2.1. Again, as I said, clarity is very important here. Otherwise, you will have trouble going over the rest of the RDTs because it's going to get a lot more complicated. Now, there's a question from Qiandi. Is it possible that the sequence number is corrupted? It is possible, but mostly when that happens, the checksum will fail. Okay, and therefore we don't need to do the sequence number check. Okay, now if the corruption passed and yet the sequence number is actually not exactly what's being sent, yeah, that will be the case. That's a little bit similar to what Caffrey was saying. Okay, so I'm assuming that Caffrey was asking corrupted NACK being the sequence number that's a duplicate. Okay, all right. And now we can move on to RDT 2.2. And given the time today remaining, we will just talk about the idea of RDT 2.2. Okay, so Xuan has a question, but let's go over the idea of 2.2 first before coming back to Xuan's question. Okay, good. RDT 2.2, it's essentially the same as 2.1, except here. It's going to be the NACK-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, okay, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like two packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have two different packet formats, just have one acknowledgement packet, but adds a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit, to indicate whether it's really a positive acknowledgement or a negative acknowledgement. All right. So same functionality as 2.1, but using only ACK packet. But the ACK packet will be carrying an extra bit that is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NACK-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0. Right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So still sending ACK packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first ACK with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 ACK. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Yeah, having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, yeah, sender is sending an ACK, right? So sender there will have to what? Retransmit the packet that's last sent. All right, so that's all the time we have. So let me address Shen's question. And we will not have time to go over the RDT 2.2 sender receivers finite state machine. Those will come first thing tomorrow morning. So Shen is asking, is there a chance the receivers might receive packets from 2 different senders at the same time? That's a very interesting question. You see, Shen, obviously in that case, things will be messed up. Therefore, for one connection, you get a pair of sender-receiver, and you run the finite state machine. You track what is the current state for the sender-receiver uniquely per transmission, yeah, per connection. So if there needs to be another sender sending some data to the same receiver, then you will actually create 2 finite state machines, and you track, okay, the current state of the finite state machines. Okay, so obviously you cannot use one receiver finite state machine to handle 2 different connections transmission. Okay, good. Yeah, so and that's all. And there's just there's one more question. Okay, we don't have a midterm break next week, am I right? No, we don't. We will go on with the lectures. Yeah, so there's something I want to say here. Yeah, now I recall. Guys, if you recall the RDT 2.1 sender machine, wow, it's huge, right? Lots of transitions. Receiver, it's also quite big. Lots of transitions. But with quiz 17 and 18, you should realize that they're just a slightly more abstract form of describing the mechanism and showing what is the next step to take for the sender, what is the next step to take for the receiver. And with that next step taken by the receiver, what will be the next step for the sender to take? Okay? If you see more finite state machines, which is coming and a lot more complex, don't feel frustrated. You just need to be a little bit patient. Okay? They are quite straightforward. You just need to read through the finite state machines and exercise a few times, a few combinations. Then you will get the idea. All right? Good. So I'll be showing you 2 more finite state machines for RDT 2.2 and 2 more finite state machines for RDT 3.0, obviously, tomorrow. Chances also high that we'll talk about pipelined protocols, pipelined RDT, and go back N is the first pipelined protocol we'll talk about. And for GBN, the go back N protocol, there are also finite state machines. Okay, so essentially tomorrow and much of next week, you will see a lot more finite state machines. Okay, hope that I did not beat you down with the RDT 2.1 stuff, finite state machines. So stay spirited and come back tomorrow morning. And right after RDT 2.2, we'll work on quiz 19. Quiz 19 is also a little bit special. It's actually a quiz to set the stage for RDT 3.0. Good. With that said, that's all the time we have. I see you tomorrow morning. Okay, bye. Okay, bye. Yeah, so here's the suggestion. Yeah, so all the lectures are recorded. So if you need more time to prepare for midterms, it's okay. You shift your time a little bit. And you can always come back to watch the videos after you're done with your exams or homeworks in case they are all lined up and you need more time. Okay, good. Bye.